All right, let's jump in. Today's class recording has started. So, last week, we were going through the quantum mechanical model of the atom. Quantum mechanical model of the atom starts with some ideas that Bohr put forth. First, what's the gist of Bohr's model of the atom?
1913.
All right, so 1913 is the most important part of it. It's not. All right, so first, we have what? Defined orbits for electrons. What do those orbits represent? Energy levels, meaning what?
They can jump up and down.
By doing what?
By
Gaining or losing energy. That the distance from the nucleus represents how much energy those electrons have. Higher orbits represent higher amounts of potential energy, lower orbits, lower amounts of potential energy. Okay? The idea that those energy levels relating to how much the location of the electron determining, or the amount of energy an electron has determining its location, sort of holds true with Schrodinger, but what's different about Schrodinger's model versus Bohr's model? Doesn't have defined spaces. What does it have? Probable locations. What do we call those probable locations? Orbitals. We call those probable places orbitals. So we said that everything on this drawing that we drew over the past couple of days is an orbital. It is a likely location or a probable location of electrons. Not all of them have the same probability. Tomorrow, we will start getting into, okay, which ones are more probable than others and blah, 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 blah. That's the next part of this situation. But these are all orbitals. These are all likely locations for electrons. So on Friday, we started working with quantum numbers. What do quantum numbers do for us? Address. In terms of these electrons, or sorry, in terms of these orbitals, what are the quantum numbers doing? What does an address do for us? Good. It distinguishes one house from all the other houses, right? What do quantum numbers do? Distinguish one orbital from all the other orbitals, right? How many quantum numbers do we need to distinguish all these orbitals? 4. Okay? So, right? Okay. Quantum numbers give us a unique way of distinguishing each orbital from all the other orbitals. Each orbital has 4 quantum numbers that is unique to that orbital and distinguishes it from all the other ones. Okay? On Friday, I believe we went through 3 of them. Is that correct? Okay. Let's review the 3 that we did. What is the first quantum number called? Joe, go ahead. What's its name first? Okay, the principal quantum number. What letter do we use to represent the principal quantum number? N. All right, here's the challenging part. Okay? Without reading directly from your outline, what does the principal quantum number tell us in a general sense? How close or far away it is, which Jasmine means, sorry, I didn't call you Jasmine, right? What does it tell us then if it tells us how close or far away it is? Generally speaking, how much energy it has. Orbitals that have lower quantum numbers are closer to the nucleus, which means they have what? Less energy, right? So generally speaking, our principal quantum number relates for us the amount of energy that electrons in those orbitals will have. Okay? All right. Next quantum number that we came across is called the what? The angular momentum quantum number. What letter do we use to represent the angular momentum quantum number? L, lowercase l. Again, without reading directly from your notes, what does the angular momentum quantum number describe for us?
Sub-level and shape.
I'm pretty sure I did not use the word sublevel at all on Friday. So
Sub-level consequence shape of
like I said, without reading directly from your outline.
You said subbable and shape, not subbable shape.
All right. Okay, so the angular momentum quantum number pretty much tells us the shape of an orbital. We went through 3 different shapes. What's the first shape that shows up in every energy level? Sphere. What do we call a spherical shaped orbital? An s orbital. All right, that one's easy to remember. S sphere. Okay. The next shape that shows up is a what? A figure 8 or a double teardrop, right? What do we call figure 8 or double teardrop orbitals? P orbitals, right? Then we get the 4-petaled flower, right? 4-petaled flowers are what kind of orbitals? D orbitals, okay? And then there's a 4th shape that's called F orbitals that has 7 complex shapes, but we aren't going to get into that, okay? So the angular momentum quantum number tells us the shape of the orbital, okay? All right, last one we talked about on Friday was the what? The magnetic quantum number. What letter? M. What does the magnetic quantum number do for us? Tells us which axis it's on, right? How many p orbitals exist in each level? 3. One on the x-axis, one on the y-axis, one on the z-axis. The magnetic quantum number distinguishes this one from this one from this one. All right? How can we tell which one is which if they're all in the same energy level and they're all the same shape? That's where the magnetic quantum number comes in handy, right? Were you going to? Okay, so we said that. Okay, we said that the magnetic quantum number, the possible values for the magnetic quantum number are based on the possible number of shapes that there are in each sublevel or each shape. How many spherical orbitals are there in any level? Just one. And that means that the magnetic quantum number for spherical orbits is always the same value. All right? How many p orbitals are there in each level? 3. So how many possible values do we have to have for the magnetic quantum number? 3, to distinguish these 3 from each other. How many possible d orbitals are there? 5. So how many magnetic quantum numbers do we have to have? 5. We have 5, so we distinguish all 5 of them from each other. Okay? Good? So far? All right. Let's go back to the picture. Let's review some things. Okay? We started here with this, the first orbital that we drew on our whole entire picture. It's small, it's close to the nucleus. The fact that it's close to the nucleus is going to mean what? Lower energy, right? So its principal quantum number, lowercase letter n, is equal to 1. It's the lowest possible energy level that electrons can have. L tells us what about the orbital? Its shape. This is a spherical orbital. All s orbitals get an L value equal to 0. And we said that how many spherical orbitals are there in each level? Just 1. So the m value, we only need one m value because we don't have multiple spheres that we have to tell apart. Okay? Good? All right. Next picture, right? We went to this part. We said that on our drawing, what relates to or what corresponds with a change in energy level? Color. A change in distance from the nucleus, yes, but we represented that with the different colors, right? So anytime we go to a different color, that represents a new energy level. That's why this red one has an energy level n equals to 2, right? But it's still what shape of an orbital? It's still a sphere. It's still an s orbital, and so L value is equal to 0. How many spherical orbitals are there? Just 1. So m is always equal to 0 if L is equal to 0. Then we got a little bit more complex, and we went to these 3, right? First, all of them are which color? Red. So they're all in the second energy level. That's why they all have n equal to 2. Okay? So, sorry, if we are trying to get into labeling things a little differently, we're just reviewing right now, but as we get a little bit farther, okay? The sheet that I gave you today, I meant you to kind of hold it, it's landscape, so it goes across the sheet. And the smallest orbital, like the S yellow sphere, I intended to be in the top left-hand corner. So that's sort of like, then you kind of move across, like the top left is the first energy level, the top right is the second energy level, the bottom left is the third energy level, and then the bottom right is the fourth energy level. So that's kind of how I intended it. But if your drawing is working for you, go with it. All right. So for this picture, right, all of these orbitals are in the second energy level. They're all red, so n equals to 2 for all of them. They're all what shaped orbitals? Double teardrop, right? That means they're, what do we call them if they're double teardrop? P orbitals. So that's why L is equal to 0, sorry, L is equal to 1 for all 3 of these orbitals, because they're all P orbitals. This is where our M values come in, right? These are all P orbitals in the second energy level. We have to have some way to tell them apart. That's where our M values came in. So I called the one on the x-axis M equals -1. I called the one on the y-axis M equals 0. And I called the one on the z-axis M equals +1 to tell them all apart. Okay? Good? Does that sound somewhat like where we were on Friday? Okay. Let's go. We talked about that there are how many quantum numbers? 4. So we've introduced 3 of them. Let's introduce the last one. We talked about this energy level. The very first one. The 1s orbital. Sorry. We talked about this orbital. The first one. The 1s orbital. The fact that it has a principal quantum number of 1 means what about it? Close to the nucleus, and that means low energy. Okay? We said that this whole drawing is determined basically by 2 principles. What are the 2 principles that lay out this entire drawing? What is this a drawing of? Orbitals, which are probable locations for electrons. What determines the quote-unquote location of electrons? 2 things. What determines how much energy it has? Distance from the nucleus. How close do electrons want to be to the nucleus? As close as they can. But what else do they have to contend with? Other electrons. The 2 principles that basically determined this whole drawing are electrons trying to be as close to the nucleus as they can, but far away from other electrons as they can. This is a very low energy state because it's close to the nucleus. But do we find a lot of electrons here? No. Why not? It's small, meaning if we put too many electrons in there, what's going to start happening? They're going to start repelling each other. And that's not low energy, that's high energy. Okay? So, all of these spaces, these likely places for electrons, have a limit as to how many electrons we can put in them. Because if we start putting too many in there, now it's not low energy anymore, and electrons go find other places. So, we find that, this is on the last page, the spin quantum number, okay? Each orbital that we put on that drawing has a capacity limit of 2. Each orbital can only hold 2 electrons. And we refer to that idea as the Pauli exclusion principle. Wolfgang Pauli. This is a German scientist who helped work on these ideas. Yeah. Well, Wolfgang is his first name, Pauli is his second name, his last name.
Like Wolfgang,
like Wolfgang Amadeus Mozart, like
So like that's like
Wolfgang is his name. Wolfgang is one word.
That's
So,
how you,
yep.
Wolf.
Like Mozart, the composer?
I know, but like, what's the
Fast.
That's his first name.
like his actual name? Like,
Mozart is his last name. We just cut like what? Yeah, people in Germany. Actually, there's a kid in my daughter's class whose name is Wolfgang. Like his parents are German, and yeah. But they call him Wolfie. You know, like Wolfie's pretty cool. Like so, like I mean, Wolfie's a pretty cool name. Like you know. So anyway, but it exists. There's people out there. So he's dead now, but you know.
Probably like in that
wait, the person in your daughter's?
No.
No.
Wolfgang Pauli is dead. So, Wolfgang Pauli is dead. Wolfgang in my daughter's class is still alive, as far as I know, unless something tragic happened today at school. So, yeah. Anyway, all right. We distinguish those two electrons from each other by giving them different spin quantum numbers. Because there are only 2 electrons maximum in each orbital, we only need 2 possible values for the spin number. So we use +1/2 or -1/2. So, let's go here. Okay. Joe, that's a good question. Why 1/2? And I literally have never thought about that before until this very moment, but I think I have an answer for you. Okay? All right. These numbers up here on the screen, these relate to the orbital. These 3 numbers relate to a space, a region around the nucleus. Okay? But the spin quantum number doesn't relate to a region, it relates to an electron. So you just learned how many electrons can this orbital hold? 2. Okay? There's the 2 electrons that exist within that orbital. Okay? So all of these numbers relate to the entire orbital itself. But I think the 1/2 is only relating to half of this orbital because it's only relating to one of the electrons within that orbital. How's that? I literally just made that up on the fly, like so. Okay, but I said I'd never thought about it before, but now I'm like, well, all of these numbers relate to the whole orbital. It doesn't matter how many electrons are in it or if there are any electrons in it. You know, this orbital exists whether there's electrons in it or not. But the spin quantum number, when we get to that S value, now it relates to a specific electron. Does that make sense? Okay, it's not good.
What determines the direction in which the electrons travel?
Spin is a misleading term. The electrons do not actually spin. We just use that to distinguish one from the other. Okay? So yeah, so don't think that they're actually spinning, right? They move, but that doesn't necessarily mean they're like, don't think of it as like the Earth rotating on its axis as it moves around the sun. That's not, yeah, it's not, yeah. That's sort of misleading, yeah, that's not what it relates to. So it's more of a quantity that we use to distinguish electrons from each other. So, which is beyond the scope of this class. So, all right, so this specific electron has a set of quantum numbers that looks like this, and then I assign a spin value to it. Joe, which spin value do you want to assign to this electron? Okay. Does it matter whether I call this electron positive 1/2 or negative 1/2? No, as long as what? Well, as long as one's positive and one's negative. So if we're talking about this electron, right, it's still in the first energy level. It's still in a spherical orbital. There's still only one spherical orbital, but now we have to distinguish that electron from the other electron. So what does this one's spin number have to be? This one has to be negative 1/2. Okay?
So the spin is just
For the electron.
The electrons within that orbital. Okay? And it really only makes a difference once we get 2 electrons within that same orbital. Joe, go ahead.
So if we were to write something like that out,
Yep.
would we have to rewrite n equals 1, L equals 0, n equals 0, and then S for either electron twice, or can we just like
Well,
two S?
well, hold on to that. I'm going to give you that. I'm going to give you something like that in just a second. Okay? All right. Do we have a good? Are we okay with our understanding of this at this point?
Can we do it for another orbital?
Yeah. I'm going to give you like. Here. Let's just jump into it. Okay. All right. Here goes. Okay.
No, no.
All right. So. Yeah. All right. So I'll walk you through. I'll walk you through 2 more, and then I'm going to turn you loose on your own. Okay.
Okay.
All right. So I'm going to make you work with each other to try and figure it out. Okay. All right. So let's start with an orbital or an electron that is right. Where am I want to put it? I'm going to put it right here. Okay. Okay. So first, this is the green level, right?
So there's only 2 for every level?
There's only 2 for each orbital.
Yes, you're doing this.
Okay. So I'm doing the green spherical one right now. Okay. All right. The fact that we moved up from yellow to red to blue and now to green means what about the energy level of this orbital? Higher. Specifically, it's the 4th energy level. So for this electron, n is equal to 4. What's going to be true about any electron that I put on this drawing? N is going to be equal to 4 to any electron that I put on this screen. Okay? Even the 4-leaf clover, because it's still it's still in the 4th energy level. It's still green. I made it green outline. That's actually a green outline. I just didn't fill it in because it was going to get too crowded. So okay. All right. What shape is the orbital that this electron is in? Spherical. So if it's a spherical orbital, regardless of what energy level it's in, what's its value of L? 0. And if L is equal to 0, what has to be true? M has to be equal to 0. What's S for this electron? Positive 1/2. Perfectly fine. Okay. Good with that so far? Go ahead. Question? Okay. So, like I said, this is the picture that I gave you guys at the beginning of class. We just did something relating to, oh, that's the x-axis thing. I don't know about that, but, okay. We just did something relating to the s orbital, right? There are 2 p orbitals in this drawing. There's this one right here, right? And there's this one right here, okay? I didn't put the 3rd p orbital on there just because it was starting to get a little too crowded, okay? It's there in real life, I just didn't put it on this drawing, okay? There is 1 d orbital on this drawing. Here it is, okay? Remember, this whole thing is a d orbital. This is 1 orbital, okay? All right, here's what I'm going to do. I am going to put 4 electrons on this paper, or on this drawing, and I want you guys to work together to come up with the quantum numbers for these 4 electrons.
Okay.
All right? Here goes nothing. All right? So, electron number 1 is here.
Okay, so.
Electron, what? Sure, I can write it 1 next to it, okay? So electron number 1 is right here. Electron number 2 is right here. Electron number 3 is right here. And electron number 4 is right here. So this, I'll call this one our example. Okay? All right. Work with the people around you. Come up with a set of quantum numbers for these 4 electrons. I will slowly start putting answers up on the board as you're working on it.
So all this stuff is n. Yeah, I know that. They're all gonna be. They're all gonna be. So they're all gonna be this one. No, not this one. This one. This one. I thought they were all the same one.
Now look where number 4 is.
Oh, I thought number 2 was number 4. Okay. So it's all the way.
Hold on.
Where'd you get that?
Don't erase anything just yet.
You're tricking me.
Not tricking you. There is more than one correct answer for this
This whole thing is
exercise.
all of this I did.
So, I don't get that. Hold on, of course it's there.
What? Good.
The only one I got wrong, we got wrong with M and number 4.
Okay.
I
Now, you
got-
maybe didn't get it wrong.
I never answered it.
Okay.
Yeah.
All right.
Okay.
Well, we only got a minute left, Edie, before the end of school, so okay. All right. Well, that was you. Okay, sorry. That was you. All right, so first. Well, wait, let's go through this first before we start hacking out. Okay, first, are we good with n equals 4 for all of them? Okay. Are we good with the L values? Okay, L value is shape. All right, let's take M. Why did I make this M equal to 0 and this M equal to 0? They're the same axis. That's the same orbital. So these two have to have the same M. But what's true about the M over here? It's got to be different. Does this one have to be -1 and does this one have to be 0 and 0? Not necessarily. That's how I wrote them in your outline, but those aren't the only different. As long as these two are the same and this one is different, that's fine. Okay? What has to be true about S for these two? They have to be different because they're in the same orbital. Going over here, M equals -2. Okay. For L, right, for d orbitals, L is equal to 2. How many d orbitals are there on your chart in your outline? 5. -2, -1, 0, 1, 2. Could have been any of those. Okay? We'll go back over this again tomorrow. We'll work on it more tomorrow.